let's now see some specialized manipulations of time series. To begin, let's briefly talk about filtering data. We'll explore this topic more completely in a later Pandas course. Here's the February sales dataset we saw earlier. Notice we provided the date column as a list in the parseDates parameter to inform readCSV to convert this column from strings to datetime objects. For now, we're not going to use the date column as the index and instead use the default integer range as an index. This data frame contains two columns of strings, company and product. We can work with the string columns as a whole using the .str attribute. This provides access to specialized string manipulation functions that get applied to every element of the Pandas series. For example, we can transform all the company names in the company column to uppercase using str.upper. Notice that the column is not transformed in place, but a new series with only uppercase letters is returned. The str attribute also provides methods to perform comparisons, such as substring searching. The str.contains method can be used to determine which rows have strings that contain the supplied substring. For example, we can search the substring where in the product column to find all of the rows that are hardware or software. Pay special attention to the fact that str.contains returns a new series of the same length as the original, but with the value true wherever the substring was found and false elsewhere. In Python, the value true is represented as 1 and false as 0. This means we can add true and false values as integers. We can exploit this feature along with string.contains to determine the number of individual sales of hardware and software products by calling .sum. This command informs us that there were 14 rows where the str.contains condition returned true. Similar to the .str attribute, the .dt attribute is used for specialized datetime transformations. For example, we can extract the hour of the day from the date column in our sales data with .dt.hour. This returns a new integer series where 0 is midnight and 23 is 11 p.m. One of these datetime transformations available with .dt is to convert between time zones with the dt.tz localize and dt.tz convert methods. For example, our company is Texas-based, so we can first localize the date column to the US Central Time Zone and assign the time zone-aware date time to the name Central. We can convert the Central series to US Eastern Times with dt.tz convert. These two operations can be performed at once using method chaining. Notice the repeated use of the .dt attribute since the tz localize returns a new series. The final manipulation we'll see here is how to interpolate values. We'll look at world population sampled every 10 years since 1960. Like the sales dataset, we have a column called date in ISO 8601 format. The values are posted on December 31st every 10 years. As seen earlier, we can use .resample to upsample the data for every year between 1970 and 2010. By extracting the first value from every decade with the first method, we see that Pandas fills in NAN for years in between. Rather than forward filling as before, it's better to use other interpolation schemes to fill the upsampled time series. The method interpolate linear, chained with .resample, applies linear interpolation to fill in values. This yields a smooth time series with a reasonable model of the yearly world population. Now it's your turn to practice string filtering, time zone conversion, and interpolation with time series in the exercises. It's time to pull together the skills you've learned so far. You're going to work now with some messy weather and climate data. For this case study, you'll be comparing observed weather data from two sources. The first is the climate normals of Austin, Texas from 1981 to 2010 from the National Oceanic and Atmospheric Administration, NOAA. This dataset consists of climate measurements for each hour of the day averaged over 30 years. The second is from Austin weather data from 2011. This also has hourly readings of many climate-related measurements like temperature, dew point, and so on. It has many unrelated measurements, missing values, and so forth. It does need to be cleaned up somewhat. You've already seen how to read data from CSV files using the Pandas Read CSV function. Remember, this includes many options for labeling columns, specifying an index, parsing dates, and interpreting missing values. Your first job in the exercises is to get those data frames in usable form for analysis. Go ahead and get started with that now. Now that you have the data loaded from the CSV files into two data frames, it's time to do some systematic statistical EDA. Both of these data frames have date-time indexes, so their columns are time series. You've seen how to slice time series selectively to pull out individual days, weeks, months, and so on. This is very important for our statistics. You've also learned a number of methods for computing statistics, including describe, mean, count, median, and others. You'll combine these with time series slicing to compute statistics over different time ranges. After all, you expect the average temperatures in January to be lower than the average temperatures in July, at least in the Northern Hemisphere. It's your turn now to do some statistical exercises with the 2011 Austin climate data and the 30-year averages for the preceding years. Finally, you can put together your time series slicing and plotting skills to do some visual exploratory data analysis. As a reminder, you've seen Pandas idioms for drawing line plots. Here's the code used to generate such a line plot. You're also now skilled at building histograms by executing code such as this. You can build many other types of plots, including box plots, which you can generate with this code here. You've also learned that Pandas builds on Matplotlib, so you can customize plots to make them nicer. This is particularly relevant with plotting time series when there are dates along the axis. Finish up the exercises now with some visual EDA. Congratulations on making it to the end of this course, Pandas Foundations. You've learned a great deal about how to work with Pandas data frames and series. You can now import many types of datasets and deal knowledgeably with a variety of import issues. You can export data to facilitate collaborative data science. You can perform both statistical and exploratory data analysis natively in Pandas, and you've used the powerful time series capabilities that Pandas has to offer. It's been a real journey. Don't let the journey stop here, however. We have another course, Manipulating Data Frames with Pandas, in which you'll learn how to leverage Pandas' seriously powerful data manipulation engine to get the most out of your data. See you there, and congratulations once again.